Problem 392 is subsequence. We are given two strings, string S and string T, and we have to check whether S is a subsequence of T and return true if it is a subsequence and false otherwise, right? Here is a definition of the subsequence. A subsequence of a string is a new string that is formed from the original string by deleting some or none of the characters without disturbing the relative positions of the remaining characters, right? So, for example, ACE is a subsequence of a BCDE, right? While this AEC is not a subsequence. So I have prepared these two strings. S is elephant and T is elegant phantom. You can probably see with this color coding that elephant is a subsequence with this definition of subsequence, is a subsequence of elegant phantom, right? Now, let's start thinking about this problem. So I think the first idea that comes to mind is that a greedy solution should work here, right? So if we, excuse me, so if we start from the first letter and try to match it, so find this letter, the earliest occurrence of this letter inside of the target, then we can mark this position because we're never going to look to the left of this position. We're going to continue, so all the search will be done to the right. So then we can go to the next letter and now start looking for L in the rest of the string, yeah? So, and here we would find the, again, earliest occurrence. It will be here, right? So again, we mark this position and the next search will be done to the right. Move to the next letter. Now, we're not going to match, so we're not going to match this E, as we said. So we're going to match this one here, right? Again, mark this position, and the rest of the search will be done here. So P then would be, this is the earliest match, yeah? So you can easily see that such a greedy solution would find something if a match exists, right? There could be multiple different matches. For example, if let's say this is P, right? So this P you can match here, or you can match potentially here. Either way, each one of these will work. But for example, if also P was in here, then there is no way you can match this one. That would not be possible. But our greedy approach would work. And I mean, the proof isn't too difficult. I don't know whether we should talk about it or not, but I think the main idea for the proof would be that the first thing you would show is that with this greedy match, yeah, let's say you're able to match some prefix, and maybe you haven't tried the rest, or the rest cannot be matched either way. But if this prefix you were able to match with this greedy approach, then any of this letter cannot be matched to any of the previous ones. So you cannot move any of these matches to the left inside the target string. So every letter would be matched to its earliest counterpart. That's the first thing to prove. And you can easily prove this with induction, okay? And after you prove that, what you can do as a second step, you could say, let's assume the following. Let's say S is a substring of T, right? Let's say a match exists, some sort of match exists which matches every letter to some letter here, right? But let's say our greedy algorithm doesn't find it, right? And then you will prove that this is impossible, which will mean if match exists, our algorithm will definitely find something. We'll find some match. And the way you would prove the contradiction is, okay, so there is a match, right? let's say you start now our greedy algorithm and you find some prefix. Now, and then you cannot continue. Our algorithm stops and cannot continue a match. Because obviously if it goes all the way to the end, then you found the match. So since we assume that this is not as the case, that our algorithm actually does not find a match, then we should say, well, it stops somewhere in the middle. Yeah. So if you look at the very last match, imagine this letter is somewhere matched in the actual solution that exists, the match which goes all the way to the end, right? So in that match, H is matched somewhere. So in our match, in one that we found with the greedy algorithm, this H cannot be anywhere to the right. It must be either exactly here or actually to the left, because we proved this in the previous step, right? But then you can definitely match A with the greedy algorithm, right? Because if in the existing match, if in the existing full match, H is here, and then you are able to match A somewhere to its right, well, in our match, in our incomplete match, this H was matched somewhere at least here, the very latest, or maybe somewhere here. So that match, which exists in the full solution, would also work for us, and we'll definitely find it. Okay? So that's our proof that the greedy algorithm works. Or at least this is a guidance how to do the proof. Get rid of everything. Now, to implement this, we're going to do, let's do a two-pointer technique, right? So within S, we have SI as an index, and we'll initialize it to index 0, pointing to this letter. And this is the letter that we're looking for. We're looking for this letter inside here. And in target, we'll have TI, the index that will initially be looking at the index 0 as again. And this is the index where we are looking for this letter. Yeah? So, and then basically what we'll do is, if these are equal, then both of them must be incremented, SI and TI. But if it's not equal, if these letters at these positions are not equal, then we only increment TI. So TI always gets incremented. We always move to the next letter, right? But SI gets only incremented when we find a match. And then when we exhaust all of these letters in the target, we'll also look at SI and see, hey, have we also exhausted all letters here? If we have, then we return true. Okay, that's the algorithm that we're gonna try to implement. Okay. So you know what? Again, copy this over to typescriptlang.org because this is a slightly better editor. So let's see. Let's create SI equals 0, TI equals 0, correct? And then let's write it like a while loop. Let's see how that works. So while SI is less than S length and TI is less than T length, correct? And now if S with an index of SI is exactly the same as T with an index of TI. So now only in this case we increment SI. Okay, that's when we increment SI. So we would increment SI only if they are equal, because we have found this letter. That means we now have to look for the next one. But TI always gets incremented. Okay? Now, I think that means we can kind of, maybe it's better to rewrite this as a for loop. So for, let's say, you know what? We're not going to need ti outside of the loop. So should I move this inside of the loop? But this looks, okay, so let ti equals 0. I'm going to move this in. Let ti equals 0. Then si is less than s length. And ti is less than t length. And plus plus ti. So ti always gets incremented. It's part of the, this is now built into the header of the loop. And here, we'll just do if the corresponding letters match, we will also increment si. So we will exit of this loop when one of these things is false, right? Either we've exhausted one string or the other, or potentially both. But what matters is whether we've exhausted si, right? So what we should say, return whether si is still less than s length. Now, actually, no. That's what we should return. So if this is a substring, then this will kick in and this will kick us out from the loop, right? Maybe we've also exhausted ti, but either way, si gets incremented, it gets to the, so it gets to point to this character. So we should be now looking for this character, but this is not actually a character. So if that happens, that means si equals the length of the string, yeah? Because of zero-based indexing. So that is our solution, right? Let's try to copy this back to our LeetCode. Wow, it looks so big. And run it on the pretests. Pretests are passed. Let's see the actual tests. Yeah, we passed. Again, nothing spectacular, just a decent pass.